Today we'll find the stiffness of a bracket with probes. We'll begin by creating our simulation files. We'll also create a linear static solution. Because we want to create a shell mesh, first we'll create a mid-surface of our sheet metal bracket. Because the bracket is a welded assembly consisting of two bodies, what we'll do is first unite the two bodies together. Then when we go to mid-surface, we'll be able to have the mid-surface automatically extend and trim between the two welded parts. And here you can see that. The gusset here has been extended and trimmed to the mid-surface of the main bracket. Now, as part of the mid-surface operation, we can tell it that we want to stitch edges. This will ensure we get a congruent mesh between the gusset and the main bracket. Now, one more thing that we'll do before we go to mesh the bracket is we'll put a point at the center of our hole. And we'll use that point a little bit later on in our finite element model creation. So next we'll go to the FEM. We'll go ahead and hide the solid representation of the bracket so we can just see the mid-surface. And because we want to include that point, we'll go into geometry options and tell it to include the point. Now, one other thing that I have set in my model display are my free and stitched edges. We can see in magenta and cyan. This allows us to more easily see where we'll get a congruent mesh and where there will be free edges. So here we can see at our butt weld joint we have magenta edges, meaning that those will be free edges and we want them to be stitched. So here we'll say stitch edge to edge, and we'll select a search and snap ends distance that's larger than those gaps between the endpoints as well as between the two lines. And here you can see now that's turned cyan, so we have it stitched. Now that the model is stitched, it's ready to be meshed. We'll put in an element size and specify mesh recipe and go ahead and mesh it. So here, if we take a closer look at the stitched edges, we can see that we have a congruent mesh. Alright, that looks good. Now, one potential source of error for the analyst is assigning the correct material properties. But here you can see we can inherit those materials that were assigned to the CAD model. If we'd like to see what material was inherited, we can do an information on the mesh, and here you can see it's Inconel. Alright, and the digital thread also helps us with assigning shell thickness. Here we can inherit that from the mid-surface, and if we'd like to see what that thickness looks like, we can turn on our element thickness and offset display to see a graphical representation of the thickness, or we can plot the thickness contours to see exactly what those thickness values are. Alright, and lastly, we'll go ahead and create a point to edge connection. Here we'll select that center point and the outer edge of our hole. Here we'd like to create an RBE2 spider. Alright, so that looks good. Let's go to our sim and we'll hide our solid representation of the bracket and create a fixed constraint on the holes on the bracket. So we'll just select the two primary holes on the bracket. And next, because we want to find the stiffness of the bracket in all three directions, we'll create three subcases. And here I've cloned the original subcase, and we'll rename the three subcases to represent the three directions that we'd like to put a load on the bracket. So here we'll put a unit load of 1 pound on the point on our secondary hole on the bracket. We'll make sure that that's in the X direction, and also just so that we can make sure we have the correct force in the correct subcase, we'll give it a name as well, force X. Alright, and then we'll activate our second subcase, statics Y, and create a unit load in the Y direction. And this time we'll change the name from force 1 to force Y. Alright, and then we'll activate our statics Z subcase and put our Z unit load into our Z static subcase. Alright, so here we can see our 3 subcases and our 3 loads. We're ready to solve. And here this solution only takes about 2 seconds to run, and we can view our results. So here we can see our results due to the load in the X direction, the Y direction, and the Z direction. We can see the different displacements that we get as a result of those 3 different loads. Now to find the stiffness of the bracket, we could just solve F equals Kx for K, so that would equal F over X, which would be 1 pound divided by the displacement in the different directions. To leverage the digital thread and reduce a potential source of error in calculating our bracket stiffness, we'll create a result probe. And in creating this result probe, we'll begin by creating a result variable, which will be the displacement in the X direction. And we'll use that in a formula to calculate our stiffness. It's our force divided by our displacement. Next, we'll specify our load case. Our first load case has a load case index of 0. That's for our static subcase X. Then we'll specify our iteration category, selection, and type. And then we'll specify the point that we'd like to evaluate our displacement at. And we want to list that value. So there you can see our stiffness in the X direction, 2,400 pounds. Let's create 2 more result probes. The next one will be the stiffness in the Y direction. Here we'll specify a result variable that will be the displacement in the Y direction, dy, and we'll use that in a formula. 1 divided by dy, and our load case index will be 1 for our second subcase, which is the statics Y. And then we'll select the same point and list, and there you can see the stiffness in the Y direction. Then lastly, we'll create our stiffness in the Z direction for our probe. We'll create a new result variable for the displacement in the Z direction. And we'll use that in our formula to calculate our stiffness. And our load case index will be 2 for our third and final subcase static Z. We'll select the same point and list, and there you can see our stiffness in the Z direction. Alright, great. Then we can select all of those probes to list, and we can see the stiffness in the X, Y, and Z direction right there in our list window. Alright, so now to show the power of the digital thread in how we have our model set up, let's go ahead and make some changes. First, we'll go ahead and remove the lightning hole in our gusset. And then we'll move the location of our secondary hole and we'll see how those changes change the stiffness of our bracket. So here you can see the mid-surface representation of our bracket has updated. Next we'll update the finite element model. And lastly here you can see that the loads have all updated to the new location of the secondary hole. Now we could just solve, but because I want to retain our original results, I'll go ahead and clone the solution, and then we'll solve the copy of the solution, the cloned copy. That just takes another second or two to run. And here you can see we have all of our probes cloned as well. And we can go ahead and evaluate them, list the stiffness in the X, Y, and Z directions, and see how that's changed from our original bracket. So here, if we want to compare those values, we can make that solution active, and then we can list those probes. All right, and there we can see the stiffness for our original bracket and our change. So that's how to calculate the stiffness of a bracket with probes.